All right, so thank you everyone, and good morning. This is Xiong from Google, and I'm here with my colleague, Krishna. And today we're going to talk about plus minus 400 volts for AI and ML racks. And I think the three things that we want to share with you, one is about, from the system application perspective, the challenges of, the rack power system driven by AI and ML. And then we'll talk about, based on our experience, some thoughts about how we can, have some solutions to work together to address those challenges. And then, we'll have call for actions for collaborations as well. Yeah, as you know, through the OCP, you have heard, all kinds of talks about the AI, ML, and the challenges. And the rack power is going exponentially, right? And, a few years ago, we talked about rack power at 20 kilowatts. But this year, GB200, we talk about 140 kilowatts per rack, right? And it's driven by the GPU or the ASIC chip. It's growing with each generation. At the same time, like we're packing more and more chips within one rack to support the ever-hungry AI model, right? And from the rack power design perspective, we do see that we are at different position of the S-curve, right? We're kind of plateaued from the power density perspective. So there's this disaggregation between the system application power growth vs the power density growth of the rack power system. Because of this, based on our projection, we do see that the existing 48 volts power system cannot support the future ML applications. And we really needed to innovate together and to drive changes in order to support the future generation of ML racks. And so here's some picture to show the rack configuration we have today. As you can see in the figure on the right, it's actually a Google rack. We have the AC/DC power conversion on the top of the rack, and then we have the BBUs or in-rack UPS at the bottom of the rack. In between, we have the payloads rack, right? And at 100 kilowatts, we have 20–30% of the space already occupied by the rack power system. And with the power continue to grow, we would expect that more and more space would be allocated for the rack power system. And then we're fighting the space with the machines, with the GPUs, right? And that's not a game that we want to be, right? So we want to do our best. We want to give all the space back to the machines so that we can optimize the performance and to have more efficient computing. And I think that the challenge of higher rack power, it's beyond just space constraints. If you look at the bus bar, the connectors, right, as also talked about by the Meta teams previously, that we are hitting all kinds of boundaries, mechanically, thermal, and the power. Yeah, so I think the signal is clear. It's time for a change, right? And I think look at the history of the Google's power design evolution. When we started 20 years ago, we have the rectifiers and the batteries in the tray. It's like laptop, right? And there's 12-volt systems. And then, with the evolution of the computing, we learned that 12 volts is not sufficient. And then, Google made that change, in the timeline of 2010, and we shift from the 12 volts to 48 volts. And also, we moved the rectifiers batteries away from the tray, right? With 48 volts, we moved the rack power system to be in the rack. And they are kind of in a consolidated pool, right? So we can optimize the performance. And then fast forward, now after 10 years, we're in 2024, and we see the exponential power growth, and it's just another time for change. So if you look at the evolution, right, the rectifiers and batteries, they're moving away from the chips, right? And because the distance is growing, so you need to increase the voltage. Otherwise, you have too much power loss or the cable would be too big, right? So from our perspective, I think the next step is really to relocate the function of the rectifier's battery to be outside of the rack. And we think the higher voltage DC is the right direction to go. And to be more specific, plus minus 400 volts. Why plus minus 400 volts, right? It's very similar to how we made the last transition, right? Why 48 volts? It's because we have pretty mature telecom, ecosystem, right? Of course, the voltage is different, it's minus 48. Actually, we started from minus 48, and later on we converted it to positive 48 volts for a good reason. And same story for the 400 volts, right? It's pretty mature thanks to the EV industry. Like we have all those components, like the semiconductors, the capacitors, all the passives, right? They're optimized for test type systems already, right? And from the other perspective, like we think 400 volts may not be sufficient for the AI and ML applications because, just look for the future. Like at some point, like we may have the high voltage plus minus 400 volt distribution in the data center, right? If we just stay at 400 volts, then potentially we'll hit like a bottleneck on the bus bar or bus duct. And then the next question is that why not just increase the voltage to 800 volts, right? Yeah, we can do that, but actually the ecosystem for the 800 volt system is less mature, right? And also, like, we should look at the end-to-end power delivery powertrain, right? So, like, we should also not forget about the machine trays in the rack, right? We need to be friendly to it. So if we have 800 volts, then we need to convert 800 volts to 54 volts and then down conversion. And based on our study, like the 800 volts to 54 volts conversion, there's a lot of penalty from the density and the efficiency perspective. And then plus minus 400 volt actually marries the benefits of the 400 volt ecosystem. And also like it can equivalent delivery like 800 volts performance. Of course, like with the plus minus 400 volts, we need 3 conductors. And then, but at this high voltage, maybe it's not a big problem to have 1 more conductor. And here, just a comparison, to look at, like what we have today, and the 48-volt rack power system vs the futuristic plus minus 400 volt rack power system, right? Like I think the 48-volt rack power system has been great. It has been serving Google pretty well, like for the past 10 years. It's very reliable, and the UPS function is distributed, and we have very small feeder domains, right? And actually, we want to leverage that idea, right? That's to facilitate the transition of the plus minus 400 volts. Basically, like we have like very similar, AC-DC conversion, and then we put the UPS function at the output of the DC, right? The only difference is that we aggregate all those AC-DC conversion and the BBU function into one rack or into one, building level conversion system. But we can have similar interactions between rectifiers and batteries. So by doing that, I think we can optimize the performance for both the power design at the same time, also like to give the most flexibility to unleash the power of the ML platform. Yeah, the transition is always difficult, right? Like because, especially of Google, we have a huge fleet and we have gigawatts of fleet. And how do we deploy this kind of plus minus 400 volt system in those old data centers where we have AC distribution, right? And also, like, let's say in the future we have new data center with a plus minus 400 volt DC. How do we deploy the 48 volt machine trays in those racks, right? Like in order to break out the dilemma, like our proposal is that we have an intermediate step, which is a sidecar solution that can, take the AC inputs and we can generate plus minus 400 volts locally for the ML racks. And also, like, we'll have 400 volts to 48 volt conversion, so that we can put it in the machine rack for those like transitions. For the sidecar rack design, there are like a few metrics that I want to highlight, right? It needs to be very cost competitive. The performance needs to be as good as what we have today, right? It needs to be very high power, high density. Otherwise, we'll occupy too much space in the data center floor, where actually we can allocate the space for the computes, right? And also it needs to be very reliable because, like for the AI models, right, they're very large and they have a very high requirements for the availability, right? And so in order to enable all those metrics, we need a higher voltage, plus minus 400 volts. So with that, I'll pass down the talk to my colleague, Krishna, and he'll talk about the comparisons of different power architectures and also the data center high voltage DC distribution.
Thank you, Xiong. Hey, everyone. All right. So looking at the architectures today, right? There are conventionally 2 types of architectures that we deploy today. So architecture 1 here kind of shows the traditional AC UPS based solution where you have your medium voltage transformer in the electrical yard that feeds the AC UPS, which then feeds the rack. So if you look at the components in this architecture, you have your AC to DC converters, traditionally in the IT racks, and then you have your batteries as part of the AC UPS that's providing support for utility sacks and swells. There's another architecture that's used today, which is more efficient. It's the OCP or V3 type of delivery, where the AC UPS is replaced essentially by BBUs within the rack itself. And we have seen a lot of talks about like the BBUs and power supplies and how they're arranged in different architectures, right? So this kind of covers primarily today's landscape in terms of delivering power from the utility down to the chip. So if you kind of go along with what Xiong talked about with the plus or minus 400 volts, there are fundamentally two ways to deliver this. One is the sidecar approach that Xiong mentioned, where you still have your medium voltage transformer, which then feeds into the sidecar with the same interface that exists today, whether it's 416 volts, 40 volts, could be even possibly 600 volts AC, right, down to the sidecar. But then the sidecar will house all your power supplies and batteries, and then feed the power in terms of a plus or minus 400 volt DC interface to the rack. Now, the North Star, and like where we would like to ultimately end up with, is something like architecture 4, where we are taking up the transformer that exists in the yard already. It is your medium voltage transformer, and combining that with the components of the sidecar. So think of it like basically an infrastructure level electrical yard transformer rectification unit, or solid state transformer, or whatever else you want to call it, right? There's so many names for it. But essentially something that converts your high voltage AC or medium voltage AC into a direct current that can be then just distributed directly to the racks at the voltage levels that are decided, in this case, plus or minus 400 volts as an example. Just looking at these four architectures, and just to compare the benefits, right, of one versus the other. So a few things that stand out is, like, if you look at the efficiency, for example, for architecture 1, again, going by fundamentals, you can see that introducing that AC UPS in line has an efficiency penalty, because you have this double conversion sort of rectification that's happening and inversion that's happening that has an efficiency penalty. Architecture 2 is sort of the optimal that is being deployed today, and then architecture 3 and 4 kind of maintains or even like possibly improves the overall end-to-end efficiency when we're looking at the power distribution. A few other things to look at is the IT rack space consumption and the data center floor. So kind of comparing all of them, you can clearly see that architecture 4 gives you the maximum space allocation, whether it's for like chips within the racks or racks within the data center hall that you need to put in. Now, obviously, it's not directly correlating with the ecosystem maturity that Xiong talked about. For architecture 3, where we're going to use like a plus or minus 400 volt option for DC with the sidecar, there is a bit of an ecosystem that already exists, so there is a lot of things we can leverage from that. And going towards architecture 4 for this larger scale power conversion from AC to DC, that is something there is a lot of work going on, a lot of research going on, and we need to sort of accelerate those efforts to deliver generally available solutions to the market. In terms of the opportunities and challenges, right, it's clear based on the previous slides that we have looked at that we can deliver energy efficiency at par or better than what it is today. Definitely space savings, because to Xiong's point, we want to put more chips. We want to put more racks, right? Anything else that takes up space, we need to try and optimize that, and ideally we need to try and eliminate it so that we can improve the density of the overall data center hall. And then obviously, this direction of plus or minus 400 volts gives you the full range of like, a 0 to 800 volt DC system in terms of power rating. So it also enables you to sort of future-proof to a certain extent for the ever-increasing densities of the racks. Now, challenges, right? As we all know, it is somewhat easy to control AC power than DC, primarily because of many fundamentals. One of them being you don't have a zero crossing when it comes to DC power systems. So things like arc flash, things like identifying ground faults in DC system become a lot more challenging and a lot more harder. And we deal with it today, but maybe somewhat within the rack. But once we start to take these systems outside the rack, we need to make sure that we're taking like a ground up sort of approach in terms of designing the system intentionally so that we're able to better detect the faults, we're able to better protect the system, and not create an environment that is any less safer than it is today for operating these. And then there's always a complexity and a cost involved when it comes to DC, just simply because of the electronics that are involved with everything. Oh, there you go, smack. Just sort of taking a step up, right? Like, so moving on. I believe microgrids will be a big part of data centers going into the future. Why? Given the fact that there are density increases that are happening, given the fact that there's sustainability that is a prime goal moving into the future, it will be very critical that we adopt a philosophy or we adopt the principles of developing data centers similar to microgrids to provide higher energy efficiency so that we can ultimately improve the overall PU of the system. We can also enable sort of seamless transition, whether you're utility connected or whether you're connected to your local on-site generation within the microgrid, without necessarily creating these sort of sags and swells or disturbances to the downstream loads, and ultimately improving the reliability and the resiliency, right? So sort of outside the data center space, this is sort of a well-matured space in terms of microgrids for whether it's petrochemical, oil and gas, different kind of industrials, and even utilities that are adopting. And primarily to protect themselves from all sorts of grid disturbances, but also to enable and integrate renewable energy sources that are cleaner sources. How does that tie into DC? Well, if you look at most of our distributed energy resources today, they do natively produce power at DC. Most of them use something called IBR, or inverter-based resources. So if you're talking about eliminating the inverter to improve the efficiency, then you can directly tie in sources like PV, wind, battery energy storage systems onto your DC bus, providing a more stable sort of power input into your racks, along with shielding your system from grid disturbances and things like that. So this is a pretty exciting field personally, and there's going to be a lot happening on this side, especially as data centers become more and more power hungry, and we're going to start to move towards on-site generation. With that, I'll pass it on to Xiong for call to action.
Yeah, so there are a few takeaways, right? Like the 48-volt power system, it's broken, and it cannot continue to support the future generation of ML racks. And so we need to make a shift and to transition to plus minus vulnerable DC. And so we're looking forward to collaboration with the community so that we can develop all those ecosystems to support the transition. With that, I think we can conclude, and we're open for questions. Thank you.
Someone's got to ask something. So I was curious, there's obviously a large ecosystem around, AC, switchgear, that type of equipment. How much needs to be developed there if we were to go towards your number 4, large-scale DC distribution?
Yeah, great question. So fundamentally, today, if we go to architecture 4, we're looking at something like a solid-state transformer. Now, solid-state transformers have been talked about, researched, and somewhat prototyped for years now across universities, vendors. Everybody I talk to have some sort of a version of prototype that's working, right? I think what we truly need to do is make those products more commercial and generally available, because there are really fundamentally 2 aspects to it. One is figuring out what that large-scale AC to DC transformation looks like at a multi-megawatt scale, right? Because obviously we don't want 500 kilowatt SSDs, because then we need to put a ton of them for a 100 megawatt data center. But we need to get into sort of the 3, 5, 6, 9 megawatt scale SSDs that can convert power at large scale. But then we also need to sort of figure out what the power distribution after that looks like in terms of the bus ducts and the fuses. Do we need circuit breakers versus can we just get away with DC fuses to protect DC for large buses? So there's a bit of a development involved there. But I think up until the SSDs, that infrastructure already exists, and what we need to focus on is SSD and beyond. And just to add to that, right, one more sort of point I'd like to sort of quickly pitch in is yes, we're talking about plus or minus 400 volt DC, great. But today, if you look at our power systems, they're also, they still have some headroom to expand, meaning on the AC side. What do I mean by that? So if you look at a 416 or a 480 volt system, you could easily, or at least mostly, take it to a 600 volt AC system, which gives you a direct roughly 40% increase in power. So that is a low-hanging fruit. You can sort of start to go after today if the power supplies are more generally supporting a 600 volt AC input, because that can be done today, right? But then from there, we can go into these much larger solutions for higher densities. Sorry, it's a long-winded answer, but hopefully that answers.
Thank you. Wonderful talk, by the way.
Thank you.
Very similar question. I know today DG Matrix announced a multi-megawatt SST to bring medium voltage directly to the rack. We've had a lot of conversations about that at the conference, and I'm curious to hear your thoughts on where the industry's at in terms of comfort level of bringing medium voltage into the data center?
Want to take it? Okay. All right, I'll take that. That's a great question, right? Again, when we're talking about like AC versus DC, I think the requirements are different. If we're talking about like bringing a 13.8 kV, AC into the data center hall, I think that presents sort of some unique challenges because that power still needs to be converted. You need to put large transformers and whatnot, right? Ideally, it would be helpful. And again, hopefully you caught one of the themes of the talk is we want to free up the space inside the hall as much as possible for the compute, right? Whether it's the chips or the racks themselves. So if we can figure out SSTs or transformer rectification units, whatever they are, to be installed outside in the electrical yard, including the batteries, because now you have a DC bus, you could directly install a battery on it, right? And really allocate that space in the hall for sort of the racks. That would be the ideal way to go. In terms of, I think, technological availability, I think I've touched on it before for SSTs, right? Today, I've seen more like maybe 1 to 2 megawatt scale, but ideally, I think to enable the densities we're looking at, we really need to scale up and get to like, 5 plus or even like close to 10 megawatts of SSTs.
Yeah, maybe to add to Krishna's
Xiong,
maybe like add to Krishna's response, right?
Oh, I see.
Like, why do we work on the plus minus fungible system, right? This is not something like we want to do a system like that and then we push it onto the machine, to the rack, right? It's a bottom-up problem. Fundamentally, it's like we don't have space in the rack, so we need to relocate the rectifier batteries to be outside the rack, and in order to do that, we need to increase the voltage. The same for the solid-state transformer or medium voltage conversion direct to the rack. I think it all depends on the problem, what's the problem we're trying to solve. If there's a need, there's a value, I think at some point it will happen naturally.
Xiong, Krishna, great presentation. Just a quick question. I know we're getting over time. I saw the architecture 3 and 4. Are you able to shed some light on the components that take from 400 volts down to 50 volts? You mentioned 400 down to CPU. Are you able to talk, what are those building blocks, or are they, get some details?
Sure. I think regarding the conversion from the plus minus fungible DC to 1 volt to the chip, right? I think the different topology architectures we can explore, and I think it's go back to fundamentals, like why do we need to do what, right? It's because of like, let's say like we do plus minus fungible to the tray, and then one idea is we can convert the voltage to 54 volts. And then after that is the system we know that we have been using for 10 years, right? So that's one approach. The other approach is that we can convert 400 volt to 12 volts and then do power distribution. So at the end of the day, it's a trade-off depends on the system, right? And so maybe it's a matter of like how much density you want to push for the module vs the power distribution on the board and the overall efficiency and the ecosystem. So, yeah.
Thank you.
All right, thanks everyone.
Thank you.